So today I want to talk about another stealer. This one was reported by my team a couple months ago, and it was a fun one to reverse. It's written in C, thankfully, so there's a lot that kind of just makes sense looking at the disassembly. But it also was obfuscated, and it did several interesting things. One of those is geofencing, like checking to see the locale of the machine it's running on, and then determining if it keeps executing based on a list that it checks against for certain countries. So want to dig into that here and also kind of explain a little bit about like queue registers in ARM and a little bit about how you can work with this logic to deobfuscate some of this. Okay, so we're going to start at this instruction, and we're focused on this function that we see called a lot. You can see the cross references here, and it looks like, just based on the fact that I've looked at this before, this ends up being the XORing instruction that this sample uses. And it takes in two values. It takes in a pointer to the encoded string, and then it takes in the size that is going to result after that. And all of these strings end up getting zero terminated. We can talk about that later. This is C, so it's going to use C strings for everything and zero terminate everything to pass its other functions. So let's start here. This instruction, what it does, this ADR instruction just moves a pointer to this address into X8. So after that, we have these queue registers that are used. Now these are interesting, and when I first looked at queue registers, I was a little bit confused. But essentially, these allow you to store 128 bits. And the reason that this is going to happen, the reason that this decided to do this is because this is a very large string and it's trying to use as little instructions as possible to put it on the stack. So whenever you see these brackets, it's like dereferencing this pointer that's inside of X8, getting the address of that, and then loading in those values into the Q0 register. So it's going to load up to 16 bytes. Then it's going to store that at this address. So this ends up being an address on the stack. X29 is the frame pointer. So stack pointer, frame pointer are, the limits of our stack in this case. And it's getting the offset here of the stack. So this negative 60 hex is going to be in between the stack pointer and the frame pointer. And it's going to store with this STUR, store those values on the stack. Then it does something that I think is pretty cool. It's pretty interesting, and it makes sense with what's trying to happen here. So it got those first 15 bytes, it appears, and then it ends up doing a calculation. So it gets the X8, the pointer that's inside of X8, it dereferences that. It gets the actual values that it's pointing to. So it would be this address plus 0xf, which ends up being this address. Binary Ninja can see that, and that's pretty cool. And it grabs all those bytes and then puts it into the Q0 register. So the Q0 register gets overwritten with these new values. And then it then does a calculation here, x29 minus 0x51, which ends up being the 0xf, the difference between hex 60 and 51. And it ends up storing those bytes at that address. Then there's a subtraction here. So all this does is get x29, the frame pointer, subtract 0x60 from there, and then store that pointer into x0. And we can see that that ends up being the beginning of where all these bytes were put. Then the value of 0x1f, which I always forget what that is, 31, gets moved into the W1 register and then gets passed into this XORing instruction. So we can just call that XOR for now. Okay, so just to make this a little bit more clear, let's look at this graph. I think this is interesting. So this is the first instruction, this ADR, right? So just to think about it like this, we have a pointer to this address. And then we're loading these bytes from this address into the Q0 register. And then we're storing that onto the stack. So these bytes get moved onto the stack. And then we end up doing the same thing again, but this time calculating the 0xf, which I believe is 15. Yeah, 15. And then we end up getting those bytes and then passing them onto the stack again. And what are these bytes? How do we know that these are the bytes that are getting moved here? So if we go back, we can go to this address and see them. We can see this 5E, 17, 3A, and so on and so forth that gets passed in, and then it gets passed in again. These are the next 15 bytes. So this ends up being 30 bytes in total that are moved in to the stack. So this kind of just helps break this down a little bit, and it just puts these next to each other. And if you look at the decompilation of this, Binary Ninja actually does a good job of showing that this is what happened. So if we kind of just scroll over, we'll see that this variable that was named big in this case, there's a built-in mem copy that we see here. Big ends up being the destination of this copying of bytes that was passed in from the source, and this ends up being 5E, 17, so on and so forth. This huge thing, which matches what we see here, this 5E, 17, 3A, 02, 00, and so on. Okay, so now we know what was passed in to this address, right? So we have this pointer, and we have all those bytes that were moved in there, and we have the length. Now let's go into the XORing instruction and just kind of see what it does. So some more ARM, which is always fun. So the first thing it does is it checks to see if x1 is 0. So x1 will be the length. So it should not be 0. If it is 0, it ends up going down here and it ends up like returning an error. So that's the first check. In ARM, x1 will be arg2 and x0 is arg1. Then there's a couple of move and move k instructions here that kind of just allow you to build on top of existing values inside of a register. So we can see x9 was given the 4EC5, so that's all the way over here. And then if you do a left shift 16 bytes, you're able to come here, and then so on and so forth. You can just kind of build on top of this. What's interesting about all of these is that they don't really mean anything, at least not for what we're trying to figure out. Okay, so here's where things get fun. So we, right, as reversers, we have to figure out like how this works, so then we can kind of create scripts or things to help us deobfuscate this and make sense of this binary a little bit better. So x0 will be that pointer to that encoded string. Since we're working with XOR, we're encoding and decoding. So that is in this register and it gets moved into x11. So this pointer gets moved into x11. So here goes encoded string move to x11. This will be our length, right? So encoded string length. So that's in x11, and if you look forward, you can see x11 is used in other places, and dereferencing, which makes sense. It's going to get those values, and it's going to do stuff with them. So the next thing that happens here, Binary Ninja sees this really well, which is awesome. We have this pointer to this address being moved into X13. This ends up being our XOR key. And you'll see why that is in a second. That gets moved into X13. So XOR key, X13. Cool. These instructions, after debugging this, I was kind of confused as to like why these even are here. So all this results in X14 getting the value of 0. Is equal to 0. X14 will end up being our index as we iterate through the bytes of the key and the encoded string. We'll get into that. Okay, so this LDRB, so this is similar to the load of values into registers, but this B at the end means a byte. So we're going to be doing a loading per byte. X11 is our encoded string. So we're going to get the first byte, and we're going to move that into W15. The reason we use these, or the reason you see this W here instead of an X, is because we're just moving a byte, and there's enough space in a 32-bit register. You don't need an entire X register, 64 bits, to have this value inside. So we are going to load byte from encoded string pointer. We know it's dereferencing because of those brackets. Okay, and now we're going to load another byte. So X13 is our key. X14 is 0 at this point. It ends up being, I guess, like an index. And we're then going to grab the first byte from there as well. So load first byte of key. Now we're going to do this EOR instruction, which in ARM is an XOR. I'm not sure why it was called EOR in this case, but this ends up XORing two values. So we have the value that's inside of W14, which ends up being this 6 in this case. And then we have the first value in our encoded string. So if we look back, it'll be like this 5E. Okay, cool. And then this ends up writing that result into W14. So XOR the first byte of key and encoded string. Result is inside of X14. So X14 now has the decoded string or byte, and it's going to then store that. So strb W14, we're going to then store that byte at the address of X11. Store this byte. Oh. Okay, X8, all the way at the top, was given this 0, and X8 ends up getting the a value of 1 added to it. So this ends up being like our count. Let me just put count here. Okay, and then X13 ends up being, let me see, this is the key, and then we're going to basically move to the next byte, in this case. Okay, so add 1 key address, and then we're going to subtract X12, this is the length, by 1, and then this subs instruction is going to make a change that then will affect flags that this branch checks for. So it does a subtraction of 1 to X12, which is our length, and if it's not equal, then you branch here, and this is going to then be our loop that is going to iterate between the key and the encoded string, and it's going to decode it based on this key. X1 is going to then be subtracted after that. once we're done, x1 is subtracted with 1, and then that is put into x8, and then we branch here. We end up storing a 0 at the end of the string. So x0 is going to still have a pointer to our encoded string. Once it's decoded, we use this x8, then we end up storing a 0 at the end. Okay, so this ends up decoding the string so that then it can use the result of this value. And we're still talking about geofencing, but we had to kind of dive into this a little bit to see how this works. The good thing is that in tools like Binary Ninja, you can kind of just create a quick script to help you with this when you're analyzing. So let's go back to the main function and let's talk about what we can do here to figure this out. So we know a couple things. We know the size, we know where this starts, and we know it's doing an XOR, and we know the key. We have like everything that we need to be able to figure out how this works. So now we have the address, the key here. We have the address, which I believe this matches, yes. And we're just using this XORing function to kind of just iterate through the bytes of both of these and then do a quick XOR, print out the result for us. So what we can do, now this is going to run. It's going to do its thing. And then we'll see we end up with this string. I believe we can also make this a little bit nicer because you can write to an address, and this address will then be this one. This should work. Writing to address, the result, and run. Awesome. So now we have these interesting strings, which, you can kind of convert this to be the locale for different countries. Now, how does it use this? That's the next thing to figure out. We know that this address here ends up being the start of these strings that are decoded and then saved on there. So what you can do, or at least what I do, is change this variable, or this stack variable. I like changing that to the string so that I can see where it's used later. And if we go down, look, and we see that it is used as the first argument that is passed to this str function. So str, locate a substring in a string, and it looks like it takes in this haystack value, which will be this string that we decoded, and then it uses a needle that is passed into x1 as the second argument, and it basically looks inside of that haystack with a needle. Interesting. Okay, so we know it's going to be used here. So now we know that this will be the haystack, essentially. Haystack. And this will be the needle. So now we need to figure out what this is. So going up, we see that this ends up being this value here that is passed into this SN printf instruction. So we need to figure out what that first argument to SN printf is. So SN printf. And down here, so just to talk about this a little bit, SN printf and these printf like format string type functions in ARM, you'll see these a little bit different. They pass their arguments into the stack, and because these are variadic functions, you'll see this ... at the end, meaning there can be multiple arguments that are passed in. So ARM chooses to use the stack for these, which makes sense. So going back, we see that this value, this x0, ends up being what's passed in here, and that will be the result of this sprintf function. And then we know that this is going to be the format string. This is going to be the length of that. And if we look up, we'll see that we have this get env with this lang string passed into it. Now you can kind of guess what this is. So like if you echo, I think this should work. This is what I get, right? So en us utf8 will then be my lang environmental variable, and we know that that matches what we see here. So we can kind of guess what's going to happen here. It's going to run this get env function. It's then going to store this on the stack. So this would be the locale env. Store that return string for the locale onto the stack. You can see this is just like the beginning of the stack. And then it's going to use this format string. It's going to do that to then write this locale at this address, which is going to be returned here. So this will be the locale result after this sprintf function works. So now if we go down, we'll see that that is how it uses this locale for these different countries. It checks the environmental variable for this from the machine, and then uses this to look inside of that haystack with that environmental variable needle. Okay, awesome. That's how this binary, this stealer, uses geofencing to determine how it wants to execute. Cool. Well, that's it.